everyone, in this video we're going to continue looking at cubic graphs. The contents of this video are a little harder than the previous video, so please make sure you watch the first video before. In this video we're going to look at the graphs of the cubic function compared with the graph of the derivative and the graph of the second derivative. Let's look at an example together. Here I've got the equation of a cubic graph. I've also drawn the graph. You can clearly see the stationary points when x is 1 and when x is 3. And also you can see the inflection point when x is 2. The equation of the first derivative is going to be 3x squared minus 12x plus 9. And the equation of the second derivative will be 6x minus 12. As you can see, the equation for the first derivative is going to give me a parabola. Now the interesting thing is, where are the x-intercepts? The x-intercepts will be when we have turning points for the original graph. So we'll have x-intercepts when x is 1 and when x is 3. Now let's consider where the original graph is increasing. When the original graph is increasing, I know that my y values for my derivative will be positive, meaning they'll be above the x-axis. That means I can finish my parabola by drawing the rest of the graph. The decreasing section of the original graph will be below the x-axis of the derivative. Next, let's look at the second derivative. We know that the second derivative is going to be a straight line. On the original graph, my concavity changes when x is 2. That means in my second derivative, I'm going to have y is 0 when x is 2. Now before 2 or after 2, I can see that my original graph is concave up, and before 2, my original graph is concave down. If my original graph is concave down, it means that my second derivative will be negative. And if my original graph is concave up, my second derivative will be positive. What you can also notice is that the turning point of the first derivative will be at the position where I've got a change in concavity. In other words, at the inflection point. Here's a second example. In this example, I have a change in concavity, but not necessarily a turning point, I just have a stationary point. I've got the equation of the graph on the left. As you can see, it would be a normal cubic graph moved 1 left and 8 up, and then I've expanded the formula. Let's quickly look at the equation of the first derivative. Again, the equation of the first derivative will be a parabola. This time the parabola will be a frowny parabola looking down. My second derivative will be a straight line. And in this case, my straight line graph has a negative gradient, meaning it will be decreasing. Now, the shape of my parabola we've already discussed, and I know that when x is negative 1, I will have a 0 value for my first derivative. In this case, for the second derivative, I have my inflection point also at negative 1. On the original graph, I know that before negative 1, the graph is concave up, and after negative 1, my graph is concave down. Meaning that on my second derivative, before negative 1, the values of my second derivative are positive, and after negative 1, the y values of my second derivative are negative. If you'd like to explore this further, I suggest you use the program Desmos. Desmos is a free application that allows you to explore many different graphs. So if I open Desmos, you'll see on the left I can choose different options, and the option I'm going to choose is calculus derivatives. Now by changing the values in my cubic graph, I can see how my derivative will change. The cubic graph is the red graph, and the purple graph is the derivative. We don't have the values for A, B, C, and D, but you do have enough here to explore how the changes to the cubic graph will change the derivative. You can clearly see where the turning points are as well as where the inflection point is and the effect on the derivative. Finally, let's look at a question from an exam paper. The question says, for a certain function f, the first derivative is given as that, clearly a parabola. Now, if I think about the shape of that parabola, the parabola will be a parabola that's smiley, or decreasing and then increasing. The first question says, calculate the x-coordinates of the stationary point of f. So let's first consider what the parabola would look like. Now I know the stationary points of f, the original graph, will be when I've got x-intercepts for the parabola. Or in other words, when my derivative is 0. So let's set the derivative equal to 0. We already know what the derivative is. We don't need to calculate it. Then I can factorize, since it's quadratic, 3x and x, plus 3 at the end and minus 1. And I can see what the values are for x. The question only asks for x coordinates, so that means I'm just going to give the x values. X is a third or x is negative 3. Let me add that to my graph. Let's look at the next question. It says, for which values of x is f concave down? Now for concave down, my second derivative would be negative. In other words, my first derivative will be decreasing. Now if I look at my graph of my derivative, I'll see that my derivative is decreasing up to the position of the turning point. So I need to work out the x value of the turning point of the graph. Now there are two ways to do this. We learnt in grade 11 that you can find the axis of symmetry using a formula, and let's look at that way first. But there's also another way. So my axis of symmetry will be minus b over 2a. I substitute the values from my derivative, which will be negative 8 over 2 times 3. And then I work out what x is. X is going to be negative 8 out of 6, which can simplify to negative 4 out of 3. So, there it is on my original graph, or on my graph of my derivative. And I can see that the x values will be less than negative 4 out of 3. So as I mentioned, there's another way to work out the axis of symmetry. If I look at the derivative of the parabola and set it equal to 0, that will give me the turning point. Since I already have a derivative, I'll need to find out the second derivative. The second derivative is 6x plus 8. And now if I solve it equal to 0, I find that I get exactly the same value for the axis of symmetry. So in future, if you're working with parabola, either you can find out the axis of symmetry using the formula, or if you'd like, you can find out the derivative of the parabola, set it equal to 0, and then solve, and that will also give you the equation of the axis of symmetry. This brings us to the next question. Determine the x values for which f is increasing. Now, f is increasing when the derivative is positive. In other words, when the y values of the derivative are positive. Looking at my parabola, those will be the arms above the x-axis. Now, to answer the question in terms of x, that means that x will be less than negative 3, or x will be greater than positive a third. Question 4 looks more complicated than what it is, and the mark allocation is somewhat inflated. I'm given the equation, and I know that the y-intercept is negative 18. So straight out, I know what d is. Now, since they've given me the equation of the derivative, let's work out the derivative in terms of a, b, and c. So I'll get 3ax squared plus b, 2b, plus c. However, I also already know what the equation is of the derivative from the original question. The original derivative they gave me was 3x squared plus 8x minus 3. Now, if I compare these two equations, I can clearly see what the value is of a. It'll be 1. The value of b, 2 times what is 8? 2 times 4. And c must be negative 3. So therefore, the equation of the cubic function will be 1 times x cubed, or x cubed, plus 4x squared minus 3x minus 18.